Okay. Our coverage of algebraic thinking starts with the idea of mathematical modeling. And what mathematical modeling is it's using a function, which is a more formal way of saying an equation, to represent a real life situation. It could be extremely complex, or it can be relatively simple. And we're going to start out with something that's relatively simple. Most of our equations that we're going to work with will be relatively simple. A pizza parlor charges $10 for a large cheese pizza plus an additional $1.50 per topping. We want to come up with a model, an equation that would give us the total cost of any pizza. And so what we'd want to do here is maybe say C for the cost. And the cost will be, well, it's $10 right away. And then we're going to add to that $1.50 for every additional topping. What operation do I want to do for every topping? Isn't that what operation do I want to do? $1.50 per topping. What do I want to do there? Perfect, Courtney. That's excellent. We want to multiply the number of toppings times $1.50. So we'll do $1.50 times t. And Courtney didn't have the zero. That's sort of an optional zero, right? 1.5, 1.50, those mean the same thing. I wrote it with that there just because, well, it's dollars and cents. I'll go ahead and take it to 2 decimal points, but what Courtney wrote is perfect. And so here's a model for how much any pizza would cost. If it had 9 toppings, we could find out how much it costs by using this mathematical model. Let's put that to use. A pizza parlor charges $10 for a large cheese pizza plus $1.50 for topping. Find the cost of a pizza with 3 toppings. Just to get us back in the swing of using a poll, we'll do a poll for here. So we're using mathematical model to answer a question. How much would a pizza with 3 toppings cost? Primarily what we're focused on here is the concept of using an equation to represent a real world situation. We'll go another 15 seconds and then talk this one through. All right, let's see where we are. Not unanimous, but definitely strong agreement. That's good news. We'll go ahead and take a look at this one. So what would the cost of our pizza be? Well, our model here is the same model we came up with just a few minutes ago, where the cost of our pizza is $10 plus $1.50 times the number of toppings. Here, we're just saying 3 toppings, so we're going to let t equal 3 and plug that in. If any of you remember evaluating functions, we're kind of, we'd be finding c of t in this particular case. You don't have to write that down. You don't have to know that. Just sort of if you're having any flashbacks to algebra, that's what we're doing here. We're finding the cost of a 3-topping pizza, which here would be 10 plus $1.50 times 3, 10 plus 450. And so the total cost of that pizza would be $14.50. If you have any questions about that, let me know. We're going to stay in mathematical modeling for a little while longer. All right. A widget factory costs $1,400 a month to operate, and the materials for producing one widget cost $18. To the nearest whole number, how many widgets can be produced in a month for $7,000? So if you have a $7,000 budget, how many widgets could you make? That's the question we're trying to answer here. If you had a budget of $7,000, how many widgets could you make? The first thing we'll start with here is our model. We're going to start out with our mathematical model. And our cost of operating this factory is $1,400 a month, plus every widget costs $18. If you see anything that doesn't make sense, you let me know. So we'll need to multiply $18 times the number of widgets. Very similar to what we had with the pizza model, where we had this base number and then we added on to it. And here, just having a factory open costs $1,400, and then every widget we make costs another $18. So we add those together to get the total cost. So there's our model. In the last example we looked at, it told us how many toppings. The equivalent here would be if it said, well, how much does it cost to make 400 widgets? And we would plug 400 in for W. But this one's a little bit different than that. Here, the 700 is not going to go in for W. Here, or excuse me, the 7,000 is our total cost. That's our limiting factor. We have $7,000 that we can, that's our top line budget. That's it. That's the max we can go. So we could set up an equation and say, okay, $7,000 is all I can spend. It's $1,400 to have it open, plus 18 times the number of widgets. We're going to solve this equation for W to find out how many widgets could be made with $7,000 as a ceiling for money. Some of you may be very comfortable with algebra, and that's great. We did a little bit last week. Some of you may or may not be. One thing we're trying to do here is we're trying to solve this equation. When we're solving an equation, what we're doing is we're finding the value of W that would make this equation true. What value for W would make this equation true? And I suppose you could use trial and error and just plug stuff in, but that would be really inefficient. Here, we want to use some algebra techniques. We're trying to get W by itself, which means we want to get the term that has W by itself. So as we look at this entire side of the equation, what we're going to do is we're going to work from outside in. We're going to peel this onion from the outside. We're going to start by peeling off that 1,400 to get the 18 times W by itself. What do I need to do to both sides of the equation to get rid of this 1,400? Excellent, Leslie. Excellent, Moylan. Excellent, Nicole. We're going to subtract 400. And like I've said last week, it's okay if somebody's quicker. The more of you that type that in, the more of you I know understand what's happening. And honestly, the more of you that I see are really comfortable with the steps of algebra, then maybe I don't break it down in great detail every single time. Because somebody's algebra may be rusty, I'll probably be pretty detailed with algebra, at least for a while. But if you're comfortable with the algebra, I think that's great. So here we're going to subtract 1,400 on the right. If we do that, that's going to get this to cancel. That was our goal here, is to get that to cancel and leave just the 18W. If we subtract 1,400 on the right, we have to do the same thing on the left and have 7,000 minus 1,400. And that's 5,600. You probably know exactly what's coming next. Now we've got this 18W over here. I want to get W by itself, so I need to get rid of 18. That's 18 times W. So what do I do to make that 18 go away? Very good, Jessica, Isabella, Nicole, Ashley, Emily, perfect. We're going to divide by 18. I'm going to divide by 18 on the right. That gets this to cancel, leaving me just the W. That's what I was trying to do, get the W by itself. If I divide by 18 on the right, I need to divide by 18 on the left. When I do that, 5,600 divided by 18 is 311.11111, and that keeps going. Now we need to have an answer here that makes sense, right? We always want to look back. Polling is 4 steps. We want to look back. How many widgets can be produced? Well, I can't produce 0.11 of a widget, even though a widget's just kind of a made-up thing. It does say right here, though, to the nearest whole number. So I'm going to round to the nearest whole number. And when we round to the nearest whole number, that's going to be the ones place. So I look one space to the right. That's 4 or lower, so we'll round this down. And the number of widgets that could be produced in a month is 311. Any questions on what we did here before I have you try one? Fantastic. All right, let's go. A widget factory costs $2,200 per month to operate, and the materials for producing one widget cost $11. To the nearest whole number, how many widgets could be produced in a month for $8,000? I'll set up a poll for this, and I'm going to let you come up with the model, come up with the equation, and solve it. Some of you may be really comfortable with algebra. If so, that's great. Some of you may not be so comfortable with algebra or are just a little rusty because you haven't seen it in a while, you haven't done it in a while. And so a little bit of practice will go a long way in those cases. And I'll be patient and careful when we go through algebra because I understand that it may not be something you've done in a little while. And so it may take a little practice to get there. One thing that you will probably find, well, I can't say for sure. One thing a lot of you may find pleasant about what we're covering this week is that it's much more direct than last week. Some of the problem solving, it took a little time to say, which way do I want to go about this? Am I going to draw a picture? Am I going to do algebra? What am I going to do here? What we're going to work on this week is a lot more there's one solid approach. There are other ways to answer these things, but really there's one approach that most of you are going to take, and that's the way we'll do it. There'll be a lot less thinking at the beginning about how do I want to go about this. We'll go another 15 seconds and then talk about this one. All right, unanimous on this one. Outstanding. Okay, well, we'll go through this one pretty quickly then, since that went about as well as possible. As we take a look here, our model, the cost is going to be $2,200 per month plus $11 per widget. So we'll multiply those together, and there's our model. Here, $8,000 is the amount of money we're able to spend for our $2,200 to open and $11 per widget. In order to get W by itself, we'll subtract 2,200 from both sides. Those will cancel, leaving 11W. And on the other side, we'll have 8,000 minus 2,200, 5,800. And then to get W by itself, we'll divide by 11 on the right, divide by 11 on the left. Those will cancel. 5,800 divided by 11 is 527.272, and that keeps going. We were supposed to round to the nearest whole number. Whole number means the ones place, so we find the ones place, look one space to the right. That's 4 lower, So we'll round this down to 527 widgets. That went great. We'll go ahead and move forward. If anybody has questions, you can ask them, but I feel like we're in a really good place with that. We may be asked to create a model from a table where we look at some values of X and we look at some values of Y, and it's our job to come up with a model to relate these two things together. Some sort of equation that has a Y in it and an X in it that makes them equal to each other. There's more than one way to go here and be correct. I'm curious. You could either tell me the relationship between X and Y here, what is it you do to get from one to the other, or type in a model for this situation that relates X and Y together, some sort of equation that relates them together. And if you don't see it yet or you're not ready yet, that's okay. I'm just kind of giving you the opportunity before I do it. This relationship is exactly what you think it is. You don't have to overthink this one. And multiply X by 6 to get Y. Moylan, that's excellent. Xochitl, we might not want to add 6 here. If we added 6, we would get 7, 8, 9. That's not working out, so we don't want to do that. I think Moylan's multiplying is the right thing here. So if we want to multiply X by 6 to get Y, yes, Courtney, it absolutely is a Y equals mx plus b situation. Yes. Okay, very good. So to multiply. So here we want to multiply X by 6 to get Y. That's how I'm translating what you've all told me. And then I'm going to run with what Courtney said there a little bit. And I'm going to take this sentence that I just wrote and turn it into an equation. So if I want to have Y, I need to multiply X by 6. So X multiplied by 6 would give me Y. Or the way we would probably write that, instead of Y equals X times 6, which is fine, but the way we would probably write that is Y equals 6X. And that would be a model that takes this information and gives me an equation that shows the relationship between X and Y. We would take X and multiply it by 6 to get Y. That's what this model says right here. If we were to graph it, Courtney, it would be a line. We're not going to do that just yet, but it would be because it's a Y equals mx plus b situation. Yep, sure enough. Any questions about coming up with a model from a table? One thing I can say is if you're asked to come up with a model from a table, it will be something relatively straightforward, simple, and obvious. It's not going to be extremely challenging as far as how do I get from this one to that one. Magic tricks. And magic should probably be in quotation marks here because it's not really magic, but I want you to try this with me. I want you to pick a number between 1 and 100 and just write that number down. We don't have to do this in a hurry. We can be patient, but any number between 1 and 100. And then once you have that, I want you to add 4 to that number. And once you have that number, I want you to multiply by 2. And I'll give you a second. If you picked a big number, I don't know if you have a calculator handy or not, but and then after you've multiplied by 2, I want you to subtract 2 from that number. And if I'm going too fast, y'all can just tell me. And then what you have next, I want you to divide by 2. And then once you have that number, what I want you to do is subtract your original number. Whatever it is you started with, subtract that. And when everybody's had a chance to do this, no matter what number you started with, I can tell you your answer is 3. Kind of feels a little bit like a magic trick because I don't know what you started with. There's probably everybody probably started with a different number. But let's take a look at this, right? So if I were just to pick the number 51 to start with, just for no particular reason, and I add 4, and multiply by 2, well, I guess I could have used a smaller number and avoided the calculator, but that's all right. 110, subtract 2, 108, divide by 2, it's 54, subtract the original number, that was 51, and sure enough, I get 3. How did I know that was going to happen? Like, I promise there's no magic here. The way that we knew this is going to happen is because of the algebra involved. Let's take a look at it together. And these are really fun, and kids love these things because they don't see it coming, and they may not know algebra yet, which makes it even better. We started out with some number, let's call it x. And to that we added 4. And then we multiply by 2. So we need to multiply the whole thing by 2. So parentheses are important here. Order of operations is going to play a role. Okay, let's see. I picked a number. I called it x. I added 4. I multiplied by 2. Now I need to subtract 2 from whatever I have. So with this whole thing, we need to subtract 2. Okay. And then this whole thing, I need to divide by 2. And then subtract the original number. How am I going to write subtract the original number? What am I going to put over here on the right-hand side of this? Subtract the original number. Excellent, Leslie. Very good. Outstanding. And being comfortable with variables and being comfortable with algebra, some of you may already be there, some may not, and that's okay. And then I need to subtract x from this whole thing. And so essentially, this list of instructions I've got over here on the left, what that translates to is this right here. And if we were to simplify that, let's see what we end up with. So let's see, to simplify this, and this is a little reminder of order of operations, which is, please excuse my dear Aunt Sally. Parentheses go first, exponents are next, multiply and divide from left to right, add and subtract from left to right. Here, there's nothing I can simplify inside those parentheses, but it sure would be nice if I got rid of them. And so anybody remember the name of the property I'm going to use to multiply through those parentheses? It's okay if you don't. We're going to talk about that later in the class. But if you happen to remember, very good, Natalie. Excellent. Distributive. Outstanding. And it looks like there's more, which is great too. So it's called the distributive property. We are going to distribute that 2 through those parentheses. The 2 needs to get multiplied by everything in there. And when we do that, then we have 2 times x is 2x. 2 times that positive 4 is a positive 8. We still have that minus 2 hanging around. We still have this 2 on the bottom, and we still have subtract x over there on the right. Now with order of operations, one of the things that, please excuse my dear Aunt Sally, is great, but one of the things that doesn't get shown there is what do you do when you have a division bar like that? When you have a division bar, it's kind of an implied set of parentheses around the top and bottom. We simplify everything on the top, simplify everything on the bottom, and then the last thing we would do is divide. So if there's any simplifying we can do, we'll do it, and there is here, so we'll go ahead and do that. We'll simplify the top. We've got, let's see, a positive 8 and a negative 2. So that's going to give me 2x plus 6. And then here's one that sometimes gives people trouble. We have this divided by 2. And if we're going to, some people look at this and think, well, I can just cancel those 2's because one's in the top and one's in the bottom. But that is not correct. And it's because of this addition sign right here. We have 2 terms on the top. And so if we want to get rid of that 2 in the denominator, which we do, we have to be able to divide that 2 into both terms. And it's because of addition and subtraction. If everything were just multiplied on top, we could cancel the 2's. But that's not the case here. This addition means we have to divide that 2 into each term. We'll do that. And so 2x divided by 2 is just x. 6 divided by 2 is 3. And then we still have this minus x hanging around over there. And now what we have left is just, well, we've got positive x and a negative x that will cancel each other out, leaving me with just a 3. And that's why no matter what you start with, you're going to end up with a 3 when this is your set of instructions. So it's not magic, it's really just algebra, but these are really fun to come up with, no doubt. And you can write them. You just have to go through the steps involved in the algebra of whatever it is you've created so that you know what you're going to end up with and can turn it into a magic trick. There are some times this semester where we're going to talk about some models, using models to represent different situations. The sort of first and most basic of those are even number models and odd number models. And can somebody tell me something that's true about any even number? And I'll just kind of write some down here. What's true about any even number? There's a lot of ways you can go here. I'm curious what you throw my way. Well, shoot, I typed it right there on the screen, didn't I? Every even number is a multiple of 2. Every even number is divisible by 2. Every even number is a multiple of 2. Rats, I didn't want to have it on there. I wanted y'all to tell me. Anyway, every even number is a multiple of 2. So if we look at 2, we could see that as 2 times 1. 4 is 2 times 2. 6 is 2 times 3. It's always 2 times something will give us an even number. And so if I wanted to create a model representing an even number, here's how I could do it. Whatever that something is represented by this bar. And then in order to make sure it's an even number, I just need 2 of them. So that's how I could represent an even number, because it's always 2 times something, no matter what that something is. If my something is this, and I have 2 of them, I know it's an even number. I have a question. How would I write an odd number? If I know an even number is 2 times something, how would I write an odd number? What do I need to do to make it an odd number? And this is not an easy question. If nobody comes up with it, that's totally fine. Some of you are thinking, if I could draw it, I could tell you. That's great. I'll give you a minute to try to think of how we might draw an odd number. If you get it, that's great. If not, I'll get us there. I'm curious, how would we draw an odd number instead of an even? If an even is 2 times something, how would we draw an odd? Okay, halves. If we cut them in half, I still have the same on top and bottom. The way we'll get to an odd number is by making sure that the top and the bottom are not the same as each other. Here's what I mean. Here we have an even number. And all I need to do to turn an even number into an odd is add 1. If I add 1, now I have an odd number. If I add 1 to 4, I have an odd number. If I add 1 to 6, I have an odd number. If I add 1 to 8, I have an odd number. So I'm going to have that even number I started with, and I'm going to add 1. And now I have an odd number. So if I say that an even number is 2 times something, then an odd number is 2 times something plus 1 more. And that's how we can have a model for an even number and for an odd number. I have no idea what these numbers are. I just know this one's even because it's 2 times something, and this one's odd because it's 2 times something plus 1. If you have questions about that, it's a great time to ask. If it makes perfect sense, that's fantastic. So there's a model for sort of a generic even and a generic odd number. With that in mind, if I were to add an odd plus an odd, what type of number does it have to be? An odd plus an odd has to be what? Okay, we got a whole lot of evens, some question marks. That's excellent because I think it's even, not 100% sure. There's a couple of ways you could answer this question of an odd plus an odd. One way, very concrete, is to use some numbers and see and just sort of convince yourself. So you could say, well, if I do 5 plus 9, I got 14. That was odd plus odd made even. Okay, what if I do 7 plus 13? Well, that's 20. Okay, odd plus odd made even. I'm starting to get convinced. Maybe one more. How about 1 plus 17? That's 8. Okay, I think I'm pretty well convinced here that odd plus odd is even. But if you wanted to do it with a model, which may be more convincing than examples, because if you were talking to a group of children, they'd say, well, it works for those numbers, but I'm not convinced it works for all of them. Okay, well, let's do the model then. So if I take this odd number right here, that I know is odd because it's an even plus one more, and then I'm going to add to that another odd number. Once I take that odd and add them together, now what I've got is something that is the same on top as it is on the bottom. So that's an even number. And so there's a way we can use the models of odds and evens to kind of show no matter what, if you take two odds and add them together, you wind up with an even. Because essentially what you've got here then is you've got the same thing on top that you've got on the bottom, and that's an even number. Exactly like a puzzle. Yeah, the two odds fit together like a puzzle, and look at that. We have an even. And you can do the same thing. If you add an even with an odd together, you can imagine these being smashed together. Well, an even and an odd is going to end up with what kind of number then? If we imagine those two smashed together, an even plus an odd is going to be what? Even plus an odd? Okay, we've got odd. Not a ton of confidence, but I like the answer, and I'd like that you're telling me the question mark is excellent. If I take this even and I add it to this odd, I end up with a number that's different on the top than it is on the bottom. And so that means it has to be an odd number because of this thing right here. So if I have this even and I add it to this odd, what I end up with has this little extra piece right here, and that makes it an odd. And you could try it. An even plus an odd gives you odd number. Even plus an odd gives me odd number. And it's because you've always got that one extra piece sticking off at the end that's going to make it odd at the end. We'll look at some other models later in the course, but for right now, that's one just of even and odd numbers, where an even number is the same on top and bottom. An odd number has that overhang. Okay, solving equations. We've looked at a little bit of this already, so this is review even from just today. But to do some solving equations, the one on the left, that's x plus 33 equals 60. If we're trying to solve this equation, we're trying to get x by itself, so we need to get rid of everything, peel everything off of there, so we need to get rid of that 33. It's plus 33, so I'm going to subtract 33 on the left to get those to cancel, leaving me x. So that accomplished the goal that I wanted to accomplish, which was to get x by itself. If we subtract 33 on the left, we have to subtract 33 on the right, and we see that x is 27. Solving the equation meant, at the very beginning, find the value of x that would make this equation true. Make this a true statement. We found that. It's 27. Y'all did really well with the algebra before, so I'll just kind of go through these. If you see something you're not sure of or you want to ask about, don't hesitate. Over on the right-hand side, Now we have 4 times x is 92. So I need to get rid of multiplication, so I'm going to divide by 4 on the left. That'll get those to cancel, leaving the x. We divide by 4 on the left, we also have to divide by 4 on the right. And we'll have 92 divided by 4, 23. Again, what we were trying to do is find the value of x that would make this equation true. We did that. For that to be true, x would have to be 23. And that's just a little review of solving equations. What we could do next is put those together. 3x minus 11 is 19. And this is similar to what we looked at before. I'm going to give you a chance to solve this one on your own, and then we'll do it together. Remember, we're trying to get x by itself, so we need to get the term by itself, so we need to peel off from the outside in. We're going to peel that onion from the outside in. Once you've solved this for x, you can type it in and let me know what you've got, and we'll see how we're doing. I will set up a poll for this one. My expectation is it's probably going to go pretty well for most of you, but it's a reminder of solving equations, and we'll just see what you come up with. X equals 10. I like both of those. I won't be fussy with the x equals, but thank you, Courtney. I know sometimes professors can be. This one is one that you might be able to do visually. Somebody who doesn't know algebra at all might be able to look at that and go, well, I don't know. If it was 30 minus 11, that would work. So x is 10. Okay, there's nothing wrong with that. We're going to do this with an algebraic approach and say, all right, I'm going to add 11 to the left so that those cancel, leaving the 3x. If I add 11 to the left, I have to add 11 to the right, and that'll be 30. And then the next step here that we've got to do to get the x by itself is divide by 3. Those will cancel. If we divide by 3 on the left, we have to divide by 3 on the right, and we find out that x equals 10. So what value of x would make this equation true? 10 would. I feel pretty confident about your ability as a group to solve equations, but if anybody's having troubles or this doesn't look familiar at all or comfortable, it's okay to ask. I want you to try one. 12x plus 180 is 384. For this one, I will set up a poll and give you a chance to solve it. We'll go another 15 seconds and then talk about this one. See where we are. Not unanimous, but almost. Definitely strong agreement. Let's take a look. If you have any questions, don't hesitate to let me know. So we're trying to get x by itself. So if we're going to get this x by itself, we need the term with x in it by itself. We need to peel off that 180 first. To get rid of that plus 180, we'll subtract 180 on the left, and we'll also subtract 180 on the right. Those will cancel, leaving 12x. And on the right-hand side, we've got 384 minus 180 is 204. In order to get the x by itself, we're going to divide by 12 on the left. Those will cancel. Divide by 12 on the right. 204 divided by 12 is 17. And so that's our solution there. The value of x that would make this equation true is 17. It seems like we're in a really good place with solving equations. This is a pretty quick one today because you all are doing so well. That's good. Next, we're going to look at inequalities. It's actually the last topic of the day. Today is about making models, looking at magic tricks and patterns, and then solving equations and inequalities. So for an inequality, we are going to do the exact same thing we do with equations, except there's one change. If we have 4 is less than 8, we'd all agree that's true. 4 is less. Oh, and inequalities, instead of having an equal sign, we're going to have less than or equal to, greater than or equal to. So that's how an inequality is going to be different from an equation. It's not necessarily equal to, it's greater than or less than. And so if we have this right here, 4 is less than 8, that's a true statement. We were solving equations just a minute ago. If we divide this by -2, so I've got 4 is less than 8, that's a true statement, and I am going to divide by -2 on both sides. Let's see. 4 divided by 2 is 2. Anybody, positive divided by a negative? Anybody remember? Positive divided by a negative will give me what? Negative, negative. Very good, Natalie, Boylan, Emily, excellent. Negative or positive divided by a negative will give me a negative. So when I do 4 divided by -2, I get -2 less than, let's see, 8 divided by -2, that is -4. And so originally, I started out up here with 4 is less than 8. If I were to put that on a number line, I've got 0, I've got 4, I've got 8. Sure enough, 4 is less than 8 because it's on the left of it. So 4 is less than 8, that's a true statement. Now what I've got down here is I've got this thing that says -2 is less than -4. Well, wait a minute, that's not right. If I look at my number line, -2 is on the right of -4, so that didn't work. When I divided by -2, now this isn't true anymore. What do I have to do if I divide by a negative? Perfect, Moylan, Natalie, great language. I like that it matched, that's fun. We are gonna flip the sign. And what they mean by flip the sign is we have to change the direction of the inequality symbol. If we multiply or divide by a negative in order to keep our statement true, because this is no good. -2 is not less than -4. So when we divide by a negative, we need to change the direction of the inequality. So when we divide here and we do 4 divided by -2, we get -2. 8 divided by -2 is -4. And because we divided by a negative, and actually if we multiply or divide by a negative, we have to flip the sign. Here we divided by a -2, so it was less than, we need to flip it and make it greater than, so that we end up with a true statement at the end, that -2 is greater than -4. And the key here is this. When we solve an inequality, we're going to do the exact same thing we do for an equation, except for this one condition. If in the solving process we multiply or divide by a negative, we have to flip the sign. You'll notice back here, well, it's just equals. There is nothing to flip. It's just going to be equals. But now that we have greater than, less than involved, we might have to change the direction of the sign. And we do that if we multiply or divide by a negative. Any questions about that before I have you try a couple? very good. Let's look at one. So, solving inequalities. 7x minus 22 is greater than 41. I'm going to set up a poll for this, give you a chance to write the solution. Might take me longer to type this one than it does you to answer it. That's okay. We're not in a hurry today. The fact that a lot of you are pretty solid in your algebra skills made today go by pretty fast. So here you just want to make sure you use the properties of algebra to get x by itself. We'll go another 30 seconds and then talk about it together. Let's see what we have. Okay, we're kind of split, 2/3, 1/3. Let's take a look at this one. Let's take a look. We better be careful here. Okay, so we're trying to solve this thing for x, which means we want to get x by itself. So the x by itself, we need the term with x by itself. We need to get rid of that 22 first. That says minus 22, so I'm going to add 22 to both sides. Those are going to cancel, leaving 7x is greater than, let's see, 41 and 22, that's 63. All the answers given in the poll had a 9. That's good news. The next thing we're going to do is divide by 7 on both sides. Divide by 7, those cancel, leaving x. Divide by 7 over there, that is 9. So what I've come up with is x is greater than 9. The only thing that's different in inequalities is if I multiply or divide by a negative, that is when we flip the sign. So let's see what I did here. The first step that I did, what was that? What was the very first step that I did in order to solve this? Perfect, Nicole. Perfect, Moylan, Jessica. Excellent. We added 22. Added 22. Did I multiply or divide by a negative? No, that was just adding. So that, no, not yet. Okay, and then the next step That was the first step. What was the next step I did to get my x is greater than 9 answer down there? And the first thing we did was add 22. What was the next thing? And it was just the second step, and everybody did it. That's how we got that 9. Divide by 7. So let's see. In the first step, we added, so we certainly didn't multiply or divide by a negative. And then in the second one, we did divide, but we divided by a positive. We only flip the sign if we multiply or divide by a negative. Here, we divided by a positive. So we don't flip the sign. It stays the same direction, and it stays x is greater than 9. The only time we flip the sign is if we multiply or divide by a negative. Adding and subtracting doesn't cause the sign to flip, and multiply or divide by a positive does not cause the sign to flip. The only time it flips is if we multiply or divide by a negative. Here we didn't do that. Sign stays the same. X is greater than 9. One thing about this answer, what it means, is we're trying to find the value or values of x that would make this equation true. What we just found is anything bigger than 9 will make this equation true. So if x is 10, it's true. If x is 41, it's true. If x is 9.02, it's true. Anything bigger than 9, when plugged in here for x, would make this equation true. And that's what we just found by finding the solution x is greater than 9. That there's an infinite number of solutions here. Anything bigger than 9 would make it true. Okay, one more inequality I want you to solve. Negative 3x plus 7 is greater than 79. I want you to solve this one, and I'll set up a poll for it. So in this one, we're just going through the problem-solving steps that are connected to algebra. We're trying to get x by itself so that we can see what our solutions would be. In inequalities, typically you don't just have one solution, you have a lot of them. Like in the last one, there's an infinite number of solutions. Anything bigger than 9 was a solution. Here, we may have a lot of solutions also. That's why you might hear the term solution set sometimes, is there's not just one answer. There could be a whole bunch of them. There's a whole set of numbers that could be a solution that would make the equation true. If you only have one answer, that is still a solution. solution set is just not a very interesting one. It's just a solution set that consists of one number. Let's go another 20 seconds on this and then talk through it. Let's see where we are. Oh, kind of split. Okay. So split again, the last one and this one. All right, that's really interesting. So let's be patient and careful as we go through this one together. So let's see. As I start this out, I'm trying to get x by itself, so I need the term with x by itself, so I need to get rid of that 7 first. I'm just going to ask you, have you throw it my way. This is the last problem we're doing today, so we have plenty of time. What am I going to do to get rid of that 7 on the left-hand side? What step am I going to take? Subtract 7. Excellent. 79 minus 7 is going to be a result of that, Courtney. You're right. Jessica, subtract 7. So I'm going to subtract 7 on the left, and I'm also going to subtract 7 on the right. These are going to cancel, leaving me negative 3x is greater than 72. And my step there was to subtract 7. Okay. One more step to go. What is it? Divide by negative 3. Perfect. We're going to divide by negative 3. So the next thing I'm going to do is divide by negative 3. You have to be careful. Working with positives and negatives can always be a little bit challenging. There was a time when I was a high school teacher, and I always felt like if kids could come to me comfortable working with add, subtract, multiply, and divide positive and negative numbers, we're home free. Because that can be a little bit of a struggle. And so be careful when you're especially multiplying and dividing, but even adding and subtracting positive and negative numbers. Here we want to divide by negative 3 on both sides. Now remember, if we multiply or divide by a negative, we have to flip the sign. And here, I am dividing by a negative. So whatever else happens, I have to flip this sign. It has to be less than. And now the numbers shake out however they shake out. On the left, I've got negative 3 divided by negative 3. Those cancel, leaving me the x. And here's where we have to be really careful here. 72 divided by negative 3. As we saw before, a positive divided by a negative is a negative. So 72 divided by negative 3 is going to be negative 24. The numbers behave the same way they would if we had an equation. When I subtract 7, I get 72. When I do 72 divided by negative 3, I get negative 24. They behave the same way they would if I had an equation. The only little condition we have to think about is if I ever multiply or divide by a negative, the sign flips. And here we divided by a negative, so the sign flipped. And then we end up with a solution of x is less than negative 24. So in order for this equation to be true, x has to be something less than negative 24. Hopefully that cleared that up because we were kind of split in our results. If you have any questions you want to ask, you absolutely can.